Thank you. So this is a joint work with Victor and Dali. So we're from Macquarie University and Data61 from Australia, and also Iseo Supera from France. So the application use case that we're looking at is we want to monitor real-time customer data because that could help us in giving some optimized services. So there are many use cases of that. So if we consider energy, you could be looking into real-time smart meter data, and if you release updated average of the neighborhood, that gives you an indication of electricity usage in that neighborhood. Similarly, for transport, you could be looking into commute times during peak hours, and there are multiple other use cases. The problem, of course, is privacy, because if we release these stats as is, it could result in privacy violations. For instance, in the case of smart meter, looking into those smart meter readings could actually tell whether someone is unusually present at home. Similarly, for transport use case, you could have a scenario where people could look into that data and guess if you went to work or not. And there are actually studies which show that you can link these readings, raw readings, to actual real-life human activities and thus violate people's privacy. So how do we release then privacy-preserving versions of these stats? So the obvious candidate is differential privacy. Most of the work in this area has been done on static databases. There has been some work in the streaming setting, real-time setting, but that's mostly in the case of binary data, in which one event is either a binary value 1 or 0. So our problem is much more involved. So we're interested in events which have associated data, which is real valued, within some publicly known upper bound B. And we want to release on a constant basis, as new event comes in, the updated sum or average at each event. And we are actually concerned with event-level privacy as opposed to user-level privacy. So how do we release this average, updated average, with differential privacy? So the obvious mechanism that comes to mind is to add Laplace noise at each new event. And of course, because B is in known public upper bound, so you'll add Laplace noise of scale B. So the cumulative error after n events would be about B times n. If we use a slightly different algorithm, which I'll briefly go through in the next slides, we can get an less error of B times log of n. The problem with both these approaches is that the error is still proportional to B. And we argue that there are many situations in which this upper bound B could either be too loose or unknown in advance. For instance, if we consider the commute times example, it's unlikely that any customer would be using the full 24 hours to be on a public train. And so most readings we expect to be below a threshold T, which we don't know in advance. So if we know this threshold, then we can actually use the second algorithm that I mentioned and have an error T times log of n, which could be a significant improvement if the ratio of B to T is large. So we actually tested this assumption that most data is concentrated well below the publicly known bound B on 2 real-world datasets. So one of them is actually public train trips dataset from Sydney, Australia. And here we had conceived an upper bound of 24 hours, and as you can see from the graph, that most commute times are well below that. Approximately 100 minutes is what looks like the maximum of train trip times. And we did the similar thing on a supermarket dataset and found that most customers would not be spending more than $300 during a supermarket visit. So Now the question is, how can we estimate this threshold with privacy? So first thing we found out that we need to actually wait until a certain number of observations, which we call the time lag. So this time lag needs to be optimized for accuracy. If we try to estimate the threshold way too early, then that would result in high outlier error. If we wait too long, then that will only give us some marginal improvement over the worst case bound B. And most importantly, if we naively estimate this threshold, then it could violate privacy. For instance, one possibility would be the maximum of the first M readings so far, but that maximum is an actual event which violates the privacy of that person behind that event. So our work is basically around how to estimate this threshold with differential privacy. And the mechanism that we propose is quite generic, so it can be used to find out moving average, but it could also be used to find moving average over a sliding window, which uses a much stronger notion of privacy than event privacy. And also it could be used to release histogram and, in general, the scale of the distribution. So just a bit of background. This is the algorithm that I mentioned before. We use this as a submodule in our algorithm. So basically what this does is if we want to find out the moving average or the sum of the first n readings of a stream, it divides that stream into subsequences in a binary tree fashion of depth log of n. So if we want to find out the sum of first n elements of a stream, we only need to find up to log n subsequences whose union equals the sum of the stream from 1 to n. So in this example, if we want to find the sum of the first 7 observations, we only need to add up the intervals that are colored black, and there are 3 of them instead of adding 7. So what that results in is that if we want to have noisy version of this or differential privacy version of this, then we only need to add noise of scale log of n. So our goal is to use this algorithm, but instead of having noise scale to B, we would like the noise scale to the threshold that we would like to compute. So this is the global mechanism. So we'll use the first M readings to estimate the threshold. Then we will release the sum of the first M readings at once using Laplace noise. And then after that, for each event, we will use the binary tree algorithm with Laplace noise to release the sum, updated sum. So the question now is, what are the choices for this threshold? So we began with some sort of false starts. So one of them, the obvious choice is, why not have a differentially private version of the maximum of the first M readings? But it turns out that the max function is highly sensitive. So that would mean that actually we would have to add noise scale to B. So that wouldn't work. And we also discarded using standard deviation of the distribution of the stream, because that would mean that we need to know some properties of the stream in advance. So what we use instead is the statistic called the p-Quantile, so which basically is a value above which only a p fraction of the values lie. So for instance, p could be 0.5%. So we need to estimate the p-Quantile of the stream with the first M readings with these inequalities satisfied. So M needs to be well below N. N is the total length of the stream. That's because if we wait too long, then this is not really a continual release of data. And similarly, M needs to be bigger than 1 over P, because that is approximately the number of readings that we need to obtain a stable estimate of the p-Quantile. So the roadmap from here is that we will first have an empirical estimate of the p-Quantile, then we'll add differentially private noise to that empirical estimate, and we will set that as a threshold. One complication here is that we can't use global sensitivity. That's because the p-Quantile itself has high global sensitivity. So instead of that, we could use local sensitivity, which basically only looks at how the function value changes around the adjacent streams of the input stream only, instead of looking at all possible pairs of streams. Unfortunately, local sensitivity itself could be highly sensitive, which means it could have big differences in adjacent or nearby streams. So instead of that, we use smooth sensitivity, which basically smooths out this local sensitivity as we go away from the input stream. So in summary, we will use the empirical p-Quantile and add Laplace noise with smooth sensitivity. Now, I've actually removed some important details in this talk. For those, you can look into the paper. One main complication is that we want both the empirical p-Quantile and the threshold to be greater than the actual p-Quantile, and that is because we want to be able to analytically bound the error due to outliers. So for utility, we look into a specific, so we want some nice distributions. And by nice, I mean distributions that are light-tailed. So light-tailed distributions are those distributions that are light-tailed, that are lighter than the exponential distribution beyond the p-Quantile. So we actually tested on the two datasets that I mentioned, the train trips and supermarket datasets, and we found that for sufficiently small p, these data distributions are indeed light-tailed. So why light-tailed? Because we show that if the distribution is light-tailed, then we get an error of t to the times log of n, which is what we wanted to do in the first place. Crucially, though, the light-tailed distribution assumption is not used in the privacy definition. It's only used for utility. So the reason why this gives us better utility is because of a nice property of the exponential distribution, that if we have the p-Quantile, we multiply that by a number, r, then that's always greater than a p-Quantile further down the distribution. And if the distribution is light-tailed, this means that we can estimate the p-Quantile, multiply that by that number r, and then set the threshold to that number at the end that we obtained. Which means we can actually compute the p-Quantile with far less time lag m, and also minimize the outlier error. For details, you can look into the paper. So the question is, what values should we use in practice? So for that, we have this metric called improvement factor, which is simply the ratio between the error from the binary tree algorithm that I mentioned before versus our method. So for epsilon, the privacy budget, as we increase, we get an increase in improvement factor, but then it drops down. That's because of the fact that any value above the threshold, we are truncating it to the threshold. And as epsilon gets larger, the threshold becomes tighter, and therefore that quantity comes into the error calculation. For the time lag, we see as we increase m around 50,000, we see a noticeable increase in the improvement factor. In the paper, we also show some heuristics on how to choose these other parameters that I mentioned, like p-Quantile and r, and also how to distribute the privacy budget between the different steps of the global mechanism. Finally, we experimentally evaluated our method on the two datasets. So for the train trips dataset, we achieved an improvement factor of 3.5, and for the supermarket dataset, we improved by a factor of 9 over the basic approach. So we mentioned that we obtain an increased utility with our mechanism as long as the distribution of the stream is light-tailed. So the obvious question is, what sort of data distribution is expected to be light-tailed? And we believe these are distributions that come from short-lived, time-constrained events. So this, apart from the examples that I used in this presentation, this could also be smart meter data or phone call durations and some other examples there as well. And this is opposed to heavy-tailed distributions, which are not directly time-constrained, like income distribution and file size in a computer. So to conclude, we have presented a way to privately estimate the bulk of a distribution, which comes in a streaming fashion. And we sacrifice utility with this time lag that we introduced. We have shown heuristics on how to choose parameters for both privacy and utility. And importantly, in the worst case, if we get a threshold that is very close to the public bound B, so we still perform better than the state of the art. And one final thing is that moving average is just used as one application. There are many applications, as I mentioned in the beginning of the presentations, that could be used, in which our mechanism could be used. All right, thank you.
So maybe one thing I'll start from my side, and probably something will get picked up, is that so you looked at the indeed average computation. The example that you consider in your discussion, so you mentioned some examples of light-tailed distribution, but the data that you got, they were from somewhere else. So do you know that your data, if the data that you considered in your experiment, that was light-tailed or?
Yeah, so I think I showed that in one of the slides, like this one here. So this is the train trips dataset, and we found a similar thing on the other dataset as well. So this is light-tailed beyond that p-Quantile. So light-tailed means it's actually, the CDF would be higher than the exponential distribution after p.
Any other question? All right, then I guess let's